Twinkle, twinkle, little star. I imagine that hundreds of thousands of generations have wondered what they are. Here I am again in my backyard, looking at the Big Dipper. On a clear, dark night, I can see around 1,000 stars. For the longest time, it was not known whether stars like these shined by their own light or whether they were reflecting the sun's light, as all the planets, moons, comets, and asteroids do. It's only in the last couple of generations that we have finally reached a point where we know what stars are. You'll recall that Copernicus first proposed a sun-centric model for the solar system, but you'll note that the outermost celestial sphere did not go away with the Copernican model. Parallax measurements showed us that the sun was at the center of our planetary system, but no one could find any parallax in the stars. Not Tycho Brahe, not Kepler, not Galileo, not even Newton. The reason it took so long is that stars are so very far away that parallax angles are just too small for the available instruments. Remember that the moon's parallax was 1/2 of a degree, but star parallax is measured in fractions of an arc second. In the 1830s, there was a race to see who could find the first stellar parallax. The astronomer Frederick Bessel won. The star was 61 Cygni. Here's how it works. If you recall, the maximum baseline for parallax measurements for planets was the diameter of the Earth. For stellar parallax, we have the diameter of the Earth's orbit around the Sun. That's an increase from around 13,000 kilometers, or 8,000 miles, to 300 million kilometers, or 186 million miles. That's 23,000 times larger. So from one side of the Earth's orbit, say in July, we take a line to the star and map the positions of the more distant stars. 6 months later, in January, we repeat the process. This gives us the angle theta. We define stellar parallax as 1/2 this angle. This would be the angle at the star with the Earth and the Sun making the other two corners of a right triangle. The math is the same trigonometry we used for finding distances to the rock in my backyard and to the planets in our solar system. Of course, this is an oversimplification. Frederick Bessel mapped 61 Cygni against the distant star background for 28 years, observing the star's ellipses that followed the Earth's orbit. In 1838, after thousands of measurements and calculations, he made scientific headlines by announcing that the parallax of 61 Cygni was 0.314 arc seconds. That gives us a distance of 98 trillion kilometers. That's 61 trillion miles. Way too far to be reflecting the sun's light. So at this point, in the middle of the 19th century, we knew that stars burned with their own light. If we were to move in a little closer to a star that had a parallax of exactly 1 second of arc, we'd find it to be 31 trillion kilometers away. That's 19 trillion miles. This distance is called a parsec. It gets its name from the first syllable of parallax and the first syllable of second. Astronomers like to use it for measuring distances to stars. If you're a Star Trek fan, you'll hear parsec used a lot in their distance discussions. As we discussed in our segment on the solar system, light travels at 300,000 kilometers per second, or 186,000 miles per second. To calculate how far light travels in a year, we simply multiply this number by the seconds in a minute, the minutes in an hour, the hours in a day, and the number of days in a year. That totals 9.461 trillion kilometers, or 5.88 trillion miles. We call that 1 light year. So 1 parsec is just over 3 light years. I'll use light years throughout this video book, but parsecs will come up from time to time. Let's take a look at some of the stars in our neighborhood, out to around 25 light years. That's about as far as stellar parallax measurements from ground-based telescopes can take us. Proxima Centauri is a dim red star. It is the nearest known star to the Sun and thought to be a third member of the Alpha Centauri system. Its average luminosity is very low, and it is quite small compared to other stars, at only about 1/8 the mass of the Sun. Astronomers predict that this star will remain for another 4 trillion years, 1,000 times longer than our Sun. Alpha Centauri A and B form a close binary system that is separated, on average, by a distance slightly greater than the distance between Uranus and the Sun. A, the main star, is bright and yellowish. B is not quite as bright and has an orange tinge. Here's a recent photograph of the Alpha Centauri binary system taken by Hubble. Turns out that half of all stars are actually binary systems like this one. And it is the orbital motion of these kinds of stars that enabled us to measure stellar mass, just like we calculated the mass of the Sun by the motion of the planets around it. These stars orbit the system's center of gravity, called the barycenter. We can observe the distance between the stars and locate the barycenter as the center of their elliptical motion. We can also observe the length of time it takes to make a full orbit, its period. This, along with Kepler's laws and Newton's gravitational equations, is all we need. Careful observations of Alpha Centauri show that the distance between the two stars is just under 24 times the distance from the Earth to the Sun, with A's distance to the barycenter being a little less than half of that. In addition, we see that the orbital period is almost 80 years. This gives us the mass of A at just over the mass of the Sun, and the mass of B at just under the mass of the Sun. For the most part, the position of stars is virtually identical from century to century. But a very small number of relatively nearby stars show dramatic motion across the sky. This is called proper motion. Its magnitude can be measured using the number of degrees moved and the distance to the star. Motion towards us or away from us is called radial motion. We define it as positive if the star is moving away and negative if it is moving closer. For nearby stars, this motion can be detected by using parallax techniques. With these two numbers, the total star motion with respect to the Sun can be calculated using the Pythagorean theorem. For example, here's Barnard's star. It's a dim red star with significant proper and radial motion. It's moving so fast that it's called a runaway star. Here's a look at Barnard's star, photographed in 1985. Its parallax measurement indicates that its distance was 5.98 light years. In this second photograph, taken 20 years later in 2005, we see that the star has moved 200 arc seconds across the sky. That's 10 seconds of arc across the sky each year. This is its proper motion. Its new distance is 5.94 light years, which gives us its radial motion. Combined, we get the full motion of the star with respect to the Sun. It moves 19.1 billion kilometers each year. That's 11.9 billion miles. So you can see why it's called a runaway star. In fact, Barnard's star is approaching us so rapidly that around 11,700 AD, it will be 3.8 light years from the Sun. And that would make it the closest star to our own. Getting back to nearby stars, here's Wolf 359. It is another dim red star. In fact, it's one of the least luminous stars known. Star Trek fans might recognize Wolf 359 as the scene of a great battle between the Federation and the Borg. Lalande 21185 is another dim red star. Recent analysis indicates that it may also be accompanied by at least 2 orbiting planets. One was confirmed in 2017. The search for planets around other stars, called exoplanets, is a major focus these days, and research is ongoing. This Hubble image shows a white Sirius A, the brightest star in our nighttime sky, along with its faint, white, tiny stellar companion, Sirius B. The 2 stars revolve around each other every 50 years. Here we have our first parallax star, 61 Cygni again. Modern measurements place the star at 11.36 light years away. So Bessel's calculation of 10.4 light years was pretty close. 61 Cygni has another claim to fame in that it was first noted to have high proper motion as early as 1792, when it got the nickname Flying Star. To add further to this uniqueness, in 1830, 61 Cygni was determined to be a binary star system with 2 orange stars. Altair is a bright white star. A recent study revealed that Altair is not spherical, but is flattened at the poles due to a high rate of rotation. Vega is a bright white star and one of the most luminous stars in the Sun's neighborhood. It has been extensively studied. It was the first star to be photographed by astronomers in 1850. It was the North Pole star around 12,000 BC and will be so again around 13,700 AD. This image of Fomalhaut, surrounded by a ring of debris, was taken by Hubble. The white dot in the center of the image marks the star's location. It's a bright white star, but the region around it is black because astronomers use the advanced camera capabilities to block out the star's bright glare so that a dim planet called Fomalhaut B could be seen. The small white box at the lower right pinpoints the planet's location. These observations offer insights into our solar system's formative years, when the planets played a game of demolition derby. So far, we've identified Wolf 359 as one of the least luminous stars in our neighborhood, and Vega as one of the most luminous, but we haven't been explicit as to what we mean by luminous. Stars have a wide range of apparent brightness as measured here on Earth. The variation in apparent star brightness is caused by 2 things. 1, stars have different intrinsic luminosity, and 2, stars are located at different distances from us. An intrinsically faint nearby star can appear to be just as bright to us on Earth as an intrinsically luminous star further away. Luminosity is what we use to put precise measurements on the idea of brightness. It measures the total amount of electromagnetic energy emitted by a star in watts. just like a light bulb. Apparent brightness is measured in watts per square meter. Because light from stars spreads out over the surface area of a sphere, we can use the inverse square law to categorize luminosity for all the stars that have parallax distance information. Take the Sun, for example. The apparent luminosity of the Sun, as measured in my backyard, is 1400 watts per square meter. If my backyard solar cells were 100% efficient, that's how much electricity each panel would create. Unfortunately, current technology is only 15% efficient, so I'm only getting around 200 watts per panel. Plugging our distance to the Sun into the inverse square law, we calculate its total luminosity. Here you can see that the answer is a very big number. Using Einstein's famous E equals mc squared, or energy equals mass times the speed of light squared, we calculate that the Sun is fusing 600 million tons of hydrogen into helium every second, and in the process converting 4 million tons of matter into energy every second. To put this into perspective, this number is equivalent to around 4 billion hydrogen bombs exploding every second. Astronomers use a more complex set of classifications for calculating brightness called magnitudes and absolute magnitudes at 10 parsecs. But for our purposes, we'll stick with luminosity. Getting back to stars, here's Pollux, a bright orange star. In 2006, it was confirmed to have an orbiting planet. Arcturus is an even brighter orange star. In fact, it is the fourth most luminous star in the Sun's neighborhood. Capella has a rich yellow color and is the third brightest star in the northern hemisphere after Arcturus and Vega. Closer examination finds that Capella is actually 4 stars organized as 2 binary systems. Castor is actually 3 sets of binary systems, with some bright yellow and some dim red stars. Since 1838, many astronomers have spent decades measuring star parallaxes, but the work is so painstaking that up until 1989, only a few hundred were measured. That's out of a total population of over 1,500 stars within 60 light-years from us. In 1989, however, the European Space Agency launched a spacecraft called Hipparcos. It was specially designed to accurately measure parallaxes without all the interference from the Earth's atmosphere. It did so for over 118,000 stars. Hipparcos is accurate to within 5 to 10% for stars within 650 light-years. So let's take a look at a few of these. HD 189733 is another binary system, with the primary star being a dim orange star and the secondary star being a dim red star. As we zoom into the star, you can see the dumbbell planetary nebula. We'll cover these objects in the next section. Hubble has made the first detection ever of an organic molecule in the atmosphere of a Jupiter-sized planet orbiting this star. The molecule is methane. Under the right circumstances, methane can play a key role in prebiotic chemistry, the chemical reactions considered necessary to form life as we know it. Aldebaran is a very bright red star. It may have a brown dwarf companion. A brown dwarf is a star that did not have enough mass to trigger fusion, so it only produces light via conventional means. This makes it very hard to see. Mizar is a bright white star. It is famous for being the first binary star system discovered. Galileo studied it extensively. These two stars take thousands of years to revolve around each other, so they were not seen to be rotating around each other in those days. It wasn't until the early 1800s that binary stars rotating around each other were seen. This turned out to be the first real evidence that gravitational influences existed outside of our solar system. Once the mass of enough binary stars were calculated, it became possible to plot mass versus luminosity on a graph. Here's what they found. Instead of having any combination of mass and luminosity, we see that stars fall in a line from low mass, low luminosity to high mass, high luminosity. But it is not linear. Each time the mass is doubled, the luminosity goes up 11 times. This relationship seems to work for most stars that aren't too massive. Note that this is an empirical relationship. We don't start with an equation and plot its graph. We observe events to create the graph, and then find an equation that would have created a graph that looks like the one or fits the one we observed. Now back to stars again. Spica is a blue star and the 15th brightest star in the nighttime sky. It's a close binary system whose components orbit each other every 4 days. Mira is a very high proper motion red star that is shedding an enormous tail of material. The tail stretches a startling 13 light years across the sky. It has released enough material over the past 30,000 years to seed at least 3,000 Earth-sized planets. Polaris is our current-day North Star, for it lies less than 1 degree from the North Celestial Pole. It is a double star system, with one being a supergiant. The supergiant is a classic Cepheid variable star. Cepheids are a critically important kind of star for our distance ladder. I'll talk more about them in a minute when we come to Delta Cepheid, the first Cepheid star completely analyzed. Antares is a bright red star, the 16th brightest star in the nighttime sky. The size of Antares has been calculated using its parallax and angular diameter. Its radius is 822 times larger than our Sun's. Launched in 2013, Gaia is a European Space Agency mission to create a three-dimensional map of our galaxy. This map shows the density of stars observed by Gaia in each portion of the sky. Brighter regions indicate denser concentrations of stars, while darker regions correspond to patches of sky where fewer stars are observed. Color representation is obtained by combining the total amount of light with the amount of blue and red light. As of April 26, 2018, Gaia has pinned down the brightness and position on the sky of 1.7 billion stars. It has also cataloged the parallax, proper motion, and color for 1.3 billion stars, and has relatively accurate distance information on 96 million stars. Hipparchus recorded parallax information for 118,000 stars. Gaia has done thousands of times more. With all this new data, astronomers will be recalibrating the parallax rung on our distance ladder for years to come. This view shows both brightness and color information of the 96 million stars selected from the Gaia catalog with the most accurate distance determinations. This shows the way the stars will move across the sky during the next 800,000 years. Now let's take a look at a few stars too far away for Hipparchus, but well within the range of Gaia. Betelgeuse is a very rich, reddish, cool supergiant star. It is also one of the largest and most luminous stars known. If it were at the center of the solar system, its surface would extend past the orbit of Jupiter. Cygni is a symbiotic star system in which a white dwarf feeds from the solar wind of a companion red giant star. Rigel is the sixth brightest star in the sky. Since 1943, this star has served as one of the stable anchor points by which other stars are classified. We have now visited a number of stars from our local neighborhood. We started with the nearest stars where parallax measurements from Earth-bound telescopes were good enough. We then moved out to the furthest reaches of the neighborhood using Hipparchus-based parallax measurements. And we went even further with Gaia. In our segment on the solar system, we extended the direct measurement and triangulation to include parallax for the planets. This segment covered how we measured stellar distance, mass, luminosity, and motion, all based on parallax techniques, just like we did with the solar system. And thanks to the Hipparchus and Gaia satellites, we know the parallax for hundreds of thousands of stars, which are relatively close to the Sun, so we can add stars to the reach of the parallax rung on our cosmic distance ladder. But if all we had was parallax, we'd know very little about our galaxy, and virtually nothing about the universe beyond. But the only thing we get from a star is its light.